Hey everybody, welcome back to Young Engineers. I hope you all had a good weekend. I hope you did some interesting stuff, and I hope you're ready to start learning about bridges. We've gone over all of the HTML we're going to go over for the semester. That isn't to say that we aren't going to revisit programming, because we are going to be doing Raspberry Pi later on and some other things like that, including Python. But as it stands, HTML is over. We're going to move on to bridge design, because bridges, yeah. Uh, it's going to involve a program called West Point Bridge Designer, which you guys might have gotten an email from Mr. Dubik about downloading. If not, that's okay. Or there might have been information I might have. If not, that's okay. We'll get to download it about midway through the lesson and see if we can't at least get started on some of Bridge Designer today. If nothing else, we'll take a look at it and we'll really get started into the nuts and bolts on Wednesday, and then we'll probably move on to another subject on by next week. So, yeah, bridges. If you're looking to design a bridge, there are a few things that you need to keep track of, namely the forces that are exerted upon that bridge, basically how the bridge is affected by outside forces, and what exactly causes those forces, what the sources of those forces might be. I swear I didn't do that on purpose. Anyway, so there are three major forces that you have to worry about as a bridge designer. The first one is compression. So compression is when you take, a material and you try and smash it. I mean, yeah. Things like aluminum cans, like empty aluminum cans, that would be an example of compression if you tried to smash it. Granted, a lot of times what happens with the can is the can crumples instead of actually everything getting all smashy. But that's usually what happens when things fail anyway, as they start to bend. But that is a pretty decent example of compression. Like if you empty a can and then try and stand on it or something like that, you are exerting compression upon the can between your, body and the ground. Now, counter to compression, you've got something that my computer isn't responding. There we go. Tension. Tension is the opposite. So, imagine taking some resistance bands or some taffy or something like that and pulling on it and, trying to pull it apart. That would be tension. It's when you've got forces that are trying to pull the material apart. And in that case, you might start getting fractures in the material. You might start, seeing things break apart. But it's not going to bend necessarily like it is with compression at failure point. It might just, break. Or it might break somewhere else. Regardless, it's going to break at the weakest point. Now, similar to tension, yet different, you've got shear. Now, what makes this different? Well, I'm glad you asked. You'll notice on compression and tension, those force arrows are basically going down right down the middle of like the center of the material. So along the strongest part of the material, where that might be connected. So it's trying to compress the material into a smaller shape, or it's trying to stretch it out into a longer shape, or whatever. With shear, you've still got the same center through the object. However, the forces are acting upon the center of the object while the center of the object doesn't move. Which sounds weird, but, maybe try, like if you ever replaced a tire and used a tire jack to try and loosen up that first lug nut, that key nut, that generally most wheels have. I'm sure there's a decent number of people here who have done that. So you're exerting all kinds of force on the the tire wrench to get that thing to turn. You can kind of think, okay, so there are some, and this is looking at it from the side, there are some tire wrenches that look something like this, right? And this is like the side angle of the tire, or the wheel, rather. So it goes in and attaches to a nut, and then your hands grab it. These are hands. Trust me on this, these are hands. Your hands grab it, and they turn it. So you've got sort of that long area that you grab onto, and you try and turn it clockwise. That can kind of be thought of as shear. Like shear is being exhibited on... Does kind of look like Pac-Man, yeah. That's a good point. It looks like a fat Pac-Man or something, I don't know. Anyway, this vertical bar right here, there is shear being exhibited on that, right? Because you can think of, your hands trying to turn it. At the same time, you've got the friction on the nut keeping the thing from turning. So, I mean, there are a few things all working together, but regardless, in the end, that is like shear, as opposed to like tension or compression. Tension would be your hands would go upwards, trying to pull apart the bar, and compression would be the opposite. They'd be moving inwards, trying to compress the bar, just like straight up or down. So yeah, that's what I mean when I say that shear can seem kind of similar to tension, because it's just kind of like tension in a direction, but the result is entirely different upon the object that the force is being exerted upon. I don't even know what's going on with that diagram by the end there. Okay, so anyway, yeah, compression, tension, and shear. These are all three forces, or these three are all forces which act upon a bridge that bridge builders have to worry about. And, if you wanted a little bit more information on that, I've got this link URL to the Forces lab. Put that in the question box so everybody can see it. These labs are helpful. They're not exactly incredibly in-depth, but they do help to sort of provide a little bit more of a visual aspect to what I'm trying to explain here, that hopefully is more enlightening than my terrible drawings. And there's the second slide. I forgot again. So, okay. So you got these three forces, but, where do they come from? I figure that answer is actually probably pretty obvious. But there might also be some things that may not necessarily be taken into account. So we'll take a look at those two. So the first one, what do you think the first one is? And when I say first one, I mean what do you think is the sort of force that's always acting up, or load is always acting upon a bridge? Force acting upon a bridge constantly would probably be like gravity or something like that, but what kind of load do you think a bridge has to contend with constantly? Cars, okay. So we got one vote for cars. Anybody else? Tension, alright. Wind, there's another one. I like these suggestions so far. So the answer to this is actually a little simpler than you might think, a little bit more obvious too. It's so obvious you don't even think about it. The bridge, as far as a load is concerned, there is one load of the bridge that a bridge always has to contend with, constantly, 24 hours a day, forever, and that is itself. It has to carry the weight of itself. and that's known as the dead load. That is the load that always exists. Um, so that's sort of job one as a bridge engineer, a civil engineer. Um, you want to make sure that your bridge won't collapse under its own weight. That's kind of an important thing. But yeah, that's a dead load is the weight of the bridge itself. And then you get another type of load. You got a live load, which is the weight the bridge is carrying. In this example, cars or the people staring at the river. Now, um, live loads come in a couple different flavors. You've got static live loads and dynamic live loads. So static live loads are when your live load isn't moving anywhere. Like, again, these people, for instance. When they're just standing there and staring at that stick off in the distance, they are a static live load. They are more weight than the bridge is used to carrying, or like more weight than the bridge itself. Let me rephrase that. They add to the weight that the bridge has to carry when you take into account that the bridge always has to carry its own weight. Wow. But, they aren't moving anywhere. And then you've got dynamic loads, which are loads that move. So, to use the car example, if the load is still, it's like a parked car on a bridge. If the load is moving, it's like a car moving across a bridge, motoring across a bridge. Moving from one point to another. Now, both of these are completely different beasts from one another, because a static load is no problem, assuming that, wherever the static load is hanging out is the strongest part of the bridge. If it's not, it can, gradually increase the stress on the bridge, generally not with bridges that you use in real life because they're excuse me, I had to sneeze. Regardless, it is something that still has to be taken into account. And then dynamic can be tricky in its own right too, because you might have points on the bridge which aren't as strong as other points. And you have to make sure that the bridge can distribute the stress to other stronger areas as something moves across it, and just sort of dissipate it. So if you've ever played like something like Poly Bridge or something like that, you'll notice that as a car moves across, you'll see the struts on the bridge turn red, and they'll just kind of like move across the bridge along with the car as it moves across, things like that. Which could be an issue if the load is still, because then it can't distribute that weight well enough. The stress lasts long enough, it builds, and everything breaks. And that's bad. So in addition to dead loads and live loads, you also have thermal loads, which are loads created by the atmosphere warming and cooling the bridge. One of those things you don't generally think about, but it's completely true. If you have an iron bridge and you have it in an area where the temperature varies wildly as it goes from hot to cold and back, it's going to cause the iron to expand and contract, and that's going to mess with the bridge's stability. It's not going to be a huge amount, but like if you when you drive your car or whatever, and then you park it, and the car sort of makes that crackling noise, that tinking noise after you turn it off. Generally, that's the car cooling down and the metal, settling and everything like that. At least, that's what I was taught. Because as metal heats up, it expands. As it cools down, it contracts again. And that can be enough to affect the stability of the metal object. It's not non-zero, I should say. There's also earthquake load. This one's pretty self-explanatory. Plates move, earth shakes, bridge falls. Hopefully not. But that's another thing that has to be taken into account is, shockwaves. Because we'll actually look at this a little bit later. Bridges have like all materials have sort of resonant harmonies to them. Frequencies, I should say, not harmonies. Resonant frequencies where, the material can basically vibrate more and vibrate to an unsafe level. It's a similar concept to, opera singers breaking wine glasses and things like that. They hit a certain note. It's not that they're loud. It's not that, it's a high pitched thing. It's actually a very specific pitch that causes the glass to vibrate so much that it basically breaks apart. Wind. Wind is another thing that can cause this kind of vibration. Uh, and there you go. Wind. This is a pretty significant force to account for, especially for, tall bridges and tall buildings, because as you go up higher into the atmosphere, the wind is faster because there are fewer things to break the wind speed. And, I mean, we've never gone up high enough with structures in order to really hit like a jet stream or anything like that. But, those things are kind of nasty. You'd have to worry about that. And similarly to the forces lab, there is a loads lab. I'll send that out. Same idea, not particularly high-tech, but it is a good way to basically take a look at these things from a visual standpoint. Putting little cartoon elephants on a bridge and stuff. Now, when you're done with the lesson today, hopefully you'll be able to, get off and tell your parents that bridges are made of many different types of materials. Because, I hope you can take that out of today. Because that's what we're going to go over next, is the building materials that bridges are made out of. In fact, there's a lot of them. Bridges are made out of a lot of different types of materials. And it's actually not as many as it looked like initially. There's just explanations on each of them. But it's important to take into account the needs of your bridge so that you can use the appropriate material. If you're building, a 5-foot pedestrian bridge over like just a little, crevice in the ground, a little tiny crevice in the ground, you're not going to need to use super, high strength steel or anything like that. That's just going to be entirely unnecessary. Conversely, the Golden Gate Bridge would have been really silly had it been built out of wood. Like, really extremely silly. That actually would have been a really impressive feat of engineering if they'd managed to do that, but I have my doubts. Anyway, the first type of material is, wouldn't you know it, wood. So, wood is nice because it's cheap. Super cheap. Just cut down a few trees, build a bridge with it. Don't have to do any kind of like mining or, material refining or anything like that. Just, I mean, there is some refining involved probably, depending. But it's cheap. It's cheap and it's easy to get. And it handles both tension and compression pretty well, because wood is fairly, malleable. It's got a spongy quality to it, so it can take tension and compression decently well. Because if something isn't malleable, it tends to be brittle. It's not exactly correct to say that it's either or, but for the most part, it's an easier way to think about it. So if it's not malleable, it tends to be brittle, which means that if it doesn't bend, it breaks. And that's actually usually something you can apply to many situations. So wood bends and moves decently with the flow, so it doesn't necessarily break from tension and compression as easily. On the other hand, it has maintenance costs, and pretty much everything out there in the world destroys wood. And that's why it has decently high maintenance costs. Wood will rot. Water will ruin wood. Bugs will ruin wood. Fire will ruin wood. Yeah, pretty quickly, in fact. You'll have to make sure that all of the individual pieces of wood are in good shape, especially the load-bearing pieces. and replace them with new pieces of wood as necessary. You know, just stuff like that. It's not ideal for that reason, for many projects. But for some, it's perfect. I'm also just, now I can't get it out of my head. How many spiders do you think are in this bridge? Ugh. On the other side, or another type of material we have is concrete. Concrete is pretty cheap. It's not that hard to make. It's basically just made out of dirt and rocks and water and, you know, stuff like that. It handles compression pretty well. It's weatherproof. That is to say, you know, it doesn't erode with, you know, winds and stuff like that necessarily. I mean, you can get potholes and things like that, but that won't be, you know, certainly wood would degrade faster than concrete in that situation. And it's also, uh, very importantly, fireproof. It will not catch fire like that bridge would, which is nice. On the other hand, it does not handle tension well, and it is impacted by thermal load. That is, heating and cooling can mess with concrete. And you can't really pull apart concrete very well. It's just going to break instead of bend or stretch, which is a problem. Next, we got reinforced concrete. So whereas this is just concrete, this is concrete with rebar in it, or like metal of some sort, or whatever. Now the pros on this one is it's still pretty low cost. I mean, you just got some sticks of metal wrapped in rock and earth and dirt and water. Pretty low cost. It handles compression and tension pretty well, because the rebar adds some extra, you know, reinforcement to it that it wouldn't otherwise have. In this case, it's not exactly that it stretches better, but the rebar makes it harder to pull on, so it has a higher point of breakage for that reason with things like tension. And it's, again, fireproof and reasonably weatherproof. On the other hand, still does not deal with thermal loads correctly. Or, well, I should say. I mean, everything deals with thermal loads correctly as far as physics is concerned, but doesn't necessarily deal with thermal loads well. Beyond that, you've got cast iron. Now, cast iron, you can form it in any shape, which is pretty nice. You know, you just mold it as you're making it. It can be made in a foundry and extruded to certain shapes and then assembled there. It handles compression pretty well because it's iron. And it's fireproof, again, because it's iron. I mean, iron catches fire, kind of. But usually it melts, and if it's hot enough outside for an iron bridge to melt, there are larger problems to deal with, like the fact that everything is probably on fire everywhere on the planet at that point in time. Or, you know, maybe localized to that area, but it's still, you know, a big problem. So fireproof, reasonably fireproof. Now the cons are it's expensive. You know, it's not that cheap to just sort of make an iron bridge. Like you can't, it's not like concrete where you can just sort of whip up a mixture, or wood where you can cut down a few trees. You've got to, you know, go through a fairly extensive process in order to be able to get the mineral ready and use it for bridge building. And it does not handle tension well. Iron is pretty brittle. Certainly more so than bronze or steel or something like that. And also, one of the really big issues is it breaks without warning, which is kind of a really big problem, just to have a bridge just kind of die one day. That's not good. You don't want your bridges to do that. So, then there's steel. And steel, like iron, can be formed in any shape. And actually, unlike iron, is pretty good against both compression and tension. So that's nice. And it is fireproof, again, and weatherproof, more so than cast iron. Because, well, cast iron can oxidize or rust. whereas it's harder for that to happen with steel. Cons are it's expensive. I mean, it's a lot of work to create steel, and so steel has a price which reflects that. But it's strong, and it looks cool, so that's nice. But yeah, um, so those are just some of the materials you can make bridges out of. But did you know you can also make bridges out of Oh, wait, hold on, Materials Lab. I jumped the gun here. Copy link URL. Another lab, this time on materials. But anyway, like I was going to say, did you know that bridges are also made out of rectangles and arches and triangles? You also have to worry about the shape that your bridge is made out of. Because depending on what shape it's in, it will distribute loads throughout its person differently, and in some cases more or less effectively. So that's, something you want to worry about. So rectangles, for instance, are the least stable. They don't distribute weight very well. Um, you'll find a lot of stress in the middle part of the bridge. It just generally makes everybody unhappy if they're trying to go across it. But, it is a thing. It's usable. It's been used for years now. It's not like rectangles are going out of style anytime soon. But beyond that, you've got arches, which are the best for compression, because they can distribute the compression weight across their entire arch, and then you can strengthen them with a buttress. This is basically just stuff you can stick up from a wall and stick it into an arch and basically make it stronger. Or from a bridge onto here and make it stronger. And then next you've got the triangle. And the triangle works really well with both compression and tension, and it's strongest at the points where all of the struts meet. Triangles are actually a very good shape for design, and they work very well. So you'll see a lot of modern bridges utilizing the triangle thing that don't utilize. Oh, never mind. I did it again. Just jumping the gun again. Anyway, there's the shapes lab, so you can compare the different shapes. Now, triangle isn't always a necessary design. Sometimes rectangles and arches work better. It's all largely down to the situation that you're in. And it's probably also fair to say that there is some sort of triangle design inside of the walls of this bridge. It's just, it also has a rectangular thing going on. Anyway, with that in mind, I'm going to go ahead and talk a little bit about the history of bridges. Yeah, history, bridges, in time. Anyway, Rome, the Roman Empire was really the first society to build great bridges. Now, it's entirely disingenuous to say that bridges did not exist before Rome. Of course they existed. They were everywhere. People were well aware of bridges. However, Rome was the first society to build, truly large bridges, and to use these bridges to connect and maintain the empire, like with aqueducts or highways or things like that. They were the first to really, get bridge building down to an art, I suppose, as well as a science. They also pioneered the arch style of bridge. Now, the arch bridge is better than... Okay, let's go ahead and... here it comes. Here comes the MS Paint. So, here's your riverbank, right? And you got water flowing through the middle right here. Boom. And then you've got an arch bridge. And let's just assume that it looks like that. This is an incredibly bad arch bridge, but pretend, it's symmetrical and, it was built by an actual civil engineer and everything like that. Now this bridge, like I said, is an arch bridge, and then you've also got a different style of bridge called the post and board bridge. Let's see the river again. And the post and board bridge might look something like this, where you've got board that goes across and, you know, your bridge handrails, because that's important. And then you've got struts which go down. And just sort of, you know, along the way and keep the bridge held up. Now, this design is better for river traffic. And why might you imagine that is? And by river traffic, I mean things going this way. Yeah, basically, Luke. That's pretty much exactly it. There aren't giant poles blocking the boats. That's, that is exactly the reason why, is because there's a nice open area that boats can go underneath, and people can go on top. And, you know, in this situation, that's not really ideal. So yeah, that's really exactly what it is. There you go. The arch reduces the obstructions. The posts and a post and beam bridge obstruct the river. Yep. That's part of the reason why I just like went to this slide real quick and came back and then started drawing it, because the answer is right there, and I tried to cover it over my other class, but as you can tell, it doesn't really do the trick to go like that. It just sort of puts it behind a green background, still makes it readable. But oh well. Anyway. Bridge building actually advanced greatly with the development of iron. I've tried that before, and I think what it is, yeah, it's not quite black enough. I don't know, I guess it depends on the picture quality after it comes through, but as you can see, the text is actually still more black than the black marker. But that is a good suggestion. And now we'll choose a nice purple color. Anyway. Yeah, bridge building, yeah, iron. I mean, it was big for a lot of things. The utilization of iron was huge for a lot of things, but it was also very good for bridge building. It allowed much more, I guess, relatively lightweight bridges to be made with less material. I mean, look at the amount of material that's used there versus on this bridge or this bridge. The parts could be assembled in a foundry and just sort of welded together when they got here, or riveted together, or whatever. So that is definitely, you know, a big improvement. It also helped that it, you know, there was enough strength in it and enough tension in it that you could create things like the suspension bridge. Suspension bridge is huge for bridges as well. Ha, no pun intended. Suspension bridges allowed you to span previously impossible lengths. Now, I mean, obviously there's still a limit to suspension bridges, but they are impressive, especially considering, you know, there is nothing in the middle here that is helping to support the bridge, and that's really the thing. I mean, you could obviously do longer bridges as long as you kept putting down posts periodically that, you know, touch the something, like the seafloor or whatever, but that's not always viable. Like, maybe in this situation, that's not exactly viable. Or maybe in the situation of the Golden Gate Bridge, not exactly viable. It could be. I mean, this is just the bay, but it might be. Well, we'll get into why suspension bridges are better in the Bay Area anyway. Yeah, Brooklyn Bridge was actually one of the first modern suspension bridges that was built to cross a great expanse. Modern suspension bridges. But I mean, look at all those cables suspending it up. That's, as you might imagine, what a suspension bridge works off of is you got these two posts on either side and something going between them that helps to keep the bridge up in the air. And of course, the Golden Gate Bridge is probably one of the most famous examples of it, one of the most iconic examples of it. Now, suspension bridges are nice because in the situation like an earthquake, um, suspension bridges are pretty flexible. So if an earthquake happens, they can just bend and sort of undulate, and that lowers the risk of them just sort of snapping. Generally, lowers the risk of them just snapping. Because again, if it's malleable, if it's flexible, if it's bendable, it generally means that it's not going to break as easily. Now, on the other hand, because suspension bridges are actually so flexible, they can actually, that can be a problem. Like the Tacoma Narrow Suspension Bridge in Washington in 1940. The wind, basically, it's in a windy part of Washington State. And the wind was such, the wind caused vibrations in the bridge. And the vibrations that the wind caused were actually, like the frequency for the bridge was actually the same, more or less the same frequency that the oscillations, or excuse me, that the, was the same frequency as the oscillations being provided by the wind. That's what I was trying to say. It's not a perfect explanation, but it's decently close. But essentially, the wind caused the bridge to vibrate in such a way that the vibrations just got worse and worse and worse, and eventually the bridge just snapped. And it's a terrible thing. It's really not good. There was thankfully only one casualty out of it, which also unfortunately was a dog that was left abandoned in the car after their owner fled the bridge. But it's good, I suppose, that something of this size, there weren't more casualties. But that is a thing that can happen with suspension bridges, is because they have a frequency of their own. And it's not the material itself, it's the frequency at which the bridge itself creates waves, because you can see like waves moving down a suspension bridge if it gets to that point. It's actually kind of crazy. And a lot of times they'll also, like if we're looking at a cross section of the bridge, they'll also get sort of a torsion thing going on in one direction or another. Like what you've got here. This is actually the bridge twisting in the middle, which is crazy. Anyway, now that we just talked about a bridge falling over, let's look at Bridge Designer. Show of hands, how many of you have already downloaded Bridge Designer? It's alright if you haven't. I just want to get some idea. Okay, cool. So, those of you who have not, what I'm going to do is I'm going to have you guys do a Google search for West Point Bridge Designer. And if it makes it any easier, it's at bridgecontest.org. But, you know, yeah. The first Google result should be the site you want to go to. And you can either click on Bridge Design Contest presented by Engineering Encounters or Current Contest Software. Current Contest Software will take you directly to the 2015 version, which we want to download. And obviously download it for either Windows or Mac. If you have Linux, you can probably download the Windows version and run it on Wine. I haven't verified that though, but it's usually that's the case. So, you know, go ahead and download it. It'll take however long to download. It's 39 megs, which means like 2 minutes with my internet, but probably 15 seconds for you guys, if that. And then install it. and we'll move from there. It should also be noted that the install that's performed by the installer is not necessarily a clean one. That is to say, you might run into some sort of weirdnesses if you run the program without restarting the computer. That being said, that's not going to happen to everybody necessarily. That might have just happened to me. So you don't have to restart the computer, just go ahead and give it a try after it installs, and it should run alright. However, if you get things like nodes don't appear or whatever, then you're probably running into the same issue. This is really weird. Nodes wouldn't appear when I clicked until I right-clicked. It never opens as an app. Like it doesn't open for you, Isaac? You have to go into folders. Are you running Windows 8, Isaac, or you're running Mac OS 10? Windows 8, okay. I mean, it should run as a regular program as opposed to an app. Because it's not an app, it's a program. Which is weird to say, but I guess the distinction between the two being the sort of Metro stuff that you can get from Windows 8 like that versus, you know, a program that you go through File Explorer or whatever and open up or have down here or whatever. But it is at least opening if you go through the file system, right, Isaac? Okay, good. Good, good, good. I just want to make sure. I was going to say that that would be an interesting little hurdle to try and get over there if it didn't open up. Alright, and show of hands who, real quick, have you guys got it installed? Okay, okay, so a couple more minutes. Well, I will take this opportunity to go over the Young Engineers Bridge Design Rules, or contest rules. So you guys might have noticed that they keep referring to competition software and stuff like that. And it's on a website called Bridge Design Contest, or Engineering Encounters Bridge Design Contest, and yada yada yada. Well, that's for, you know, civil engineering. Oftentimes, you know, they have local and larger contests and things like that. And we're going to have one of our own. So you'll find most of the rules on the 2015 West Point Design Competition website. Just in case, you know, you want to go into more detail on that kind of stuff. But basically, as it stands, you have to use the 2015 Bridge Design Contest software, which shouldn't be an issue for you guys, considering, you know, you all have either downloaded it or are downloading and installing it now. And the least expensive bridge wins. So basically, you build a cheap bridge that works. And we'll go more into what works exactly means. In the event of a tie, however, in least expensive bridge, whoever submits their bridge earlier wins. So, you know, fast and cheap, basically. Which is a lot like real life, when you get right down to it, fast and cheap. So, yeah. We'll have a 7th and 8th grade winner. That is to say, the 7th and 8th grade classes are actually all one class. It's a middle school class. So among all of the middle school classes, there will be one winner. And among all the high school classes, there will be one winner. So there will be 2 winners total. You guys are up against my other high school class. I'm gonna pitch you guys against each other. You gotta, everybody's gotta do better. Um, and the winners receive a $20 gift certificate to Adafruit, which is pretty cool. Adafruit is a Arduino and Raspberry Pi accessory uh, manufacturer. So they make stuff like motor shields and distance sensors and infrared sensors and just all kinds of stuff. Speakers, push buttons, whole kits that you can use to pimp out your Arduino, things like that. So you'll receive a $20 gift certificate to that. And then post your scores on Edmodo. So you can submit as many scores or as many designs as you'd like. You don't have to, just submit one. If you submit one and then you like another one better, then go ahead and submit the other one. That's all fine. But put your scores in Edmodo, and we'll go over what scores means in a minute here, or either later on today or Wednesday. Now, also please note that the winner will have to submit screenshots showing the number of iterations in their design. So that's kind of an important point. You got to make sure you got some screenshots showing how much your design changes over time. Just, as a cool thing. But also to make sure that you've gone through some form of the engineering process and haven't just copied the bridge from online or something like that. Unless you're some sort of bridge building prodigy and you get it on the first try. That might be a little hard to explain though, through the internets like this. There is a link to download the 2013 version, which is not what we're using. And let's go ahead and spend a few minutes going over the creation process for a new bridge and everything like that, and then we will call it a day. Ask the poll questions, call it a night, and then we'll meet up again on Wednesday. But for now, we'll go through the initial bit of the process because we have the time for that. Confusingly, it's just called Bridge Designer 2015. West Point doesn't feature into the name at all, so if you're like me on Windows 8.1 or whatever and you have to do a search for it, typing in West Point is not going to turn up anything. You gotta type in Bridge Designer 2015, or maybe just start typing Bridge and it'll come up. West Point, the U.S. Military Academy, was the first school in the U.S. to offer a formal program of instruction in engineering. The Bridge Designer began as a faculty project to celebrate the Military Academy's bicentennial in 2002. 200 years, right? Yeah, 200 years. So 1802. Wow. Anyway, that's where the West Point comes from, as in West Point, the Military Academy. That usually comes up with tips, but that wasn't exactly a tip, that was just a thing. But you can just click close on that, and it'll bring you up a new thing. You've got create a new bridge design, or load a sample bridge design, or load an existing bridge design file. What we're going to do is we're going to create a new bridge design. But the whole idea is to design a truss bridge that costs as little as possible while still passing the load test with no member failures. That is to say, costs as little as possible, has a couple of trucks drive across it, and stuff doesn't fall off your bridge. Because again, if you've ever played Polybridge, you get those situations where like you have to build a jump for a monster truck or whatever, and then the monster truck will drive off the jump, and then the bridge will just sort of crumble behind it, but it'll still make the jump and everything's okay and cool. And it'll say that you passed the level, and we're really going to fly here. You got to make sure that, the bridge doesn't really fall apart every time a car drives across it, because that makes for an expensive bridge. But yeah, we're going to select create a new bridge design and hit OK. And you're going to get this, read the design requirement. Design requirement. As a civil engineer working for the State Department of Transportation, you are responsible for designing a truss bridge to carry a 2-lane highway across the river valley. Your objectives are: 1. To ensure the bridge can carry its own weight. to include the weight of the reinforced concrete deck plus the weight of a standard truck loading, and 2, to keep the cost of the project as low as possible. So basically, your bridge has to not fall over and be as cheap as it possibly can be. Or like bend or anything like that. Too much. But yeah, so we got the cross section of the river. As you can see, we're gonna have to span 44 meters, and it's gonna be 24 meters up. We've also got a deck cross section up here, but that'll show up later. And then you've got a site cost down here and some tips. The site cost will increase in price over time for various reasons, and the site cost, before you even place down a single node, will actually have money in there. It will not start at $0.00 by the time you start building your bridge. And we'll see why in a minute. But go ahead and click Next. Then you got Enter Local Contest Information. Are you participating in a local bridge design contest? Just go ahead and click No. You don't have to worry about that. Just move on to the next one, number 3. Select the deck elevation and support configuration. Now you'll notice here that a bridge has appeared in the elevation view. So we've got a deck, and the deck is basically just the thing that the trucks drive across. That's all that means. That's just a fancy name for the road that is a part of the bridge that, everything moves across. It's called the deck because usually there's some sort of reinforcement below the deck, which, keeps it from falling over. But anyway, you can change all kinds of things about this. You can change the abutments, which are these things over here on the sides. You can make them so they're arch abutments, and they'll take the, the arch, which is nice. You've got a pier, which is like the post and board design. You can raise that so that there's more to, support the bridge. You can have cable anchorages if you'd like, so you can create a suspension bridge of some sort. And you can even change the elevation of the deck itself all the way down. Now, hilariously, you'll notice that there is this right here, this little, if this pattern is there, it's called excavation. You'll notice that the bridge may be the shortest there, but the cost goes from $62,700 with all these options standard to $134,000, because part of the cost involves digging out the friggin' valley in order to get a bridge this low, which I think is just ridiculously silly. Yeah, sure, your bridge will be cheap, but also no, it won't be. So we're going to keep all these things at standard. So 24 meters, standard abutments, no pier, and no cable anchorages. We're going to do that for now. For the contest, you can use, what you'd like. But for our examples and just to see how a bridge gets created, we're going to use the standard options. Now, if you click down here, you've got site cost and site condition. You can click an arrow next to it, which gives you a breakdown of how much everything costs so far. Because as you can see, we're already at $62,000. So the deck costs $51,000, and the abutments each cost $5,500 for a total of $11,000. Good to know. Now you can see the deck cross section has appeared, and you can change some things about it, like you can put in high strength concrete, which is more expensive, but is also thinner and presumably lighter, or you can put in medium strength concrete. You can't put in low strength concrete because we're not amateurs here. We're building bridges for serious. And the loading, there's either the standard 225 kilonewton trucks with 2 lanes or the 480 kilonewton permit loading centered. We're going to deal with the standard 225 kilonewton. So, with all those things in mind, you can click Next. And one final thing. I'm glad I went through all of this just so we can get to the poll questions at the end there. But anyway, you've got through truss and deck truss, and each one of them in 3 different types. You've got Howe, Pratt, and Warren, and Howe, Pratt, and Warren. And these just basically relate to the type of This is just a template that you can draw on top of. So that's all that means. Nothing is actually created here by this other than a nice little template that you can draw on top of to give yourself a good idea of, how your bridge is supposed to be structured. So for this example bridge, we're going to select through truss. How? Hit next. Fill in the title block, optional, design by. You can do, your name or Young Engineers of Today. I'm going to do, let's see here, Chewy. Hit next. So to design the truss, we're going to click on the Finish button to activate the drawing board. We're going to draw the joints, and draw the members, then run the load test, and then strengthen any members that fail during the load test, and optimize the design by minimizing its cost, so on and so forth. Optimize the design, then fix, weak spots, then optimize the design, then fix the weak spots, so on and so forth until you have a bridge that's cheap and will not fail. Now, with that in mind, I'll just show you real quick just the basic tools here. You've got a calculator at the top, which constantly tells you an updated cost of the bridge. And you've got the various tools which you can use to build the bridge. For instance, this one that we have selected right now is the joint tool, which allows you to... Oh no, it's happening again. Place joints down. Now mine is looking all wonky because mine is doing the visual bug again. But if I right click, the stuff will appear. So as you can see, I'm filling in these gray circles at the top with joints. And then you've got the member tool, which allows you to draw from one joint to another joint, like so, just by clicking and dragging. Boom, boom, boom. And just drawing over all of these gray lines. And if you'd like, you can drag from one side to another, which, does its best to connect all of the joints in between. And this is, wow, the super bare bones basics of Bridge Simulator. Once you've got something built, you can run it with the simulator up here, which looks like a train on a bridge for some reason, and watch it fail horrendously because we haven't really spent any time improving upon the design. We'll go over all the stuff that means and what just happened here on Wednesday, but for now I am going to throw out the poll questions. Just a couple of them this time so that you guys have those answered, and then more than welcome to ask any questions you have, and if you don't have any questions at that point, you're more than welcome to head out.